So final will be released Monday. What's the date on Monday? 11, 12, 13, right? 13th, Saturday, Sunday, Monday. Due Monday, 20th December by 9 a.m. The final should not take more than 3 hours if you're prepared. Probably 2 hours is a fair amount of time, but you can take as much as you wish, which means those of you who have special requirements and have already confirmed all that, there won't be any special consideration here because it's already so much time that is being given to everyone. So you can do it whichever way you want. This deadline is very strict. If you have something going on that weekend before the exam, I cannot help it. You have to submit it before. There will be a Google form that will be included in the final, and you have to go and upload your exam there. The best way to do it is to write it on paper, take a photo, and combine all the photos of all pages into one file. Okay, the final will be accepted only as one file. I do not want 8 different files uploaded. It makes it hard for us to grade. So you have to take a photo, combine everything. You probably did something like that last semester, right? Or semester before. So, and if you have typed it out, you really don't have to, and it's not going to make any difference. Just write it on paper, and then upload to Google Form. Okay, so let's do a big picture recap of the key concepts that we have studied this semester in PChem that I hope will help you not just in the final in joining the dots, but also things that you will remember over the coming years and hopefully decades. So PChem, if you think about it, is really the study of equilibrium, right? What happens to things? What happens to materials when they come to equilibrium? What happens to chemicals when they come to equilibrium? And we studied different types of equilibrium. We studied chemical equilibrium, we studied thermal equilibrium, we studied mechanical equilibrium, right? We first studied mechanical and thermal equilibrium. It took us some time before we got to chemical equilibrium. And the big, you can call it almost the theorem or almost, I don't know, it's the big, is the statement that you do not challenge in 481. The statement is that at equilibrium, before we get to that, I guess before we get to that statement, one point we need to make is that in general, pressure, volume, temperature, number are 4 variables needed to characterize a system, a chemical system, right? When I say number, and if it's a multi-component system, then you have number of A, number of B, number of C, it becomes a vector, right? But these 4 are sufficient. So the big statement in Chem 481 and in thermodynamics is that at equilibrium, only 3 of 4 variables are needed to characterize a system. In other words, there exists an equation connecting all 4 variables, right? And anytime you have an equation connecting all 4 variables, you can, if you know the value of 3 of those variables, the 4th one is given by the equation, right? So that you cannot specify all 4 independently. And what is the meaning of such an equation existing? It really means that equilibrium is a constraint on the system. Equilibrium forces the system to be a certain way. And such an equation, we then talked about the name for such equation. Anyone remembers? Equation of state, right? Such an equation. So physical chemistry or thermodynamics really is starting with this point that equation of state exists at equilibrium. If the material is not in equilibrium, if the chemical is not in equilibrium, then there is still an equation of state, but it won't be applicable. So at equilibrium, you must follow equation of state. So at this point, we talked a little bit about what is pressure. We talked about the kinetic model of gases, right? And we understood that temperature. I'm not going to write down everything on the screen. Some things I will just talk about, because if I try to write down everything, we won't get anywhere. So we talked about temperature being something that arises from random motion of the molecules in the box, right? So temperature and pressure both arise from motion of molecules. But there was a difference that temperature really arises from the speed squared of the molecules, the kinetic energy of the molecules, while pressure arises from how quickly molecules are bombarding against the wall, right? This was the difference between them. Pressure arises from bombarding against the wall, and temperature is the kinetic energy. Did I? Well, now what I said is correct, right? Good. Good. Temperature is the kinetic energy, so temperature is related to V square, while pressure is related to change of V, right? This was the idea. And we then spent some time looking at different equations of state. The first one that you have all studied in the past also is ideal gas law, PV is equal to nRT. We talked a little bit about what goes into such an equation being applicable. The molecules have to be point-like, collisions have to be elastic. And then we also talked about other equations of state. We talked about van der Waals equation of state. And anytime you forget how to write down van der Waals equation of state, just think about the assumptions. The two assumptions van der Waals equations of state makes is, first of all, there is a finite volume of every particle. So instead of V, we write V minus NB, where B is the volume of every single molecule, is equal to nRT, but this is not sufficient. On top of this, we have to account for the fact that molecules do have an attractive force affecting them even at a very long distance. This attractive force manifests itself as van der Waals interactions in real chemicals. So that leads us to attractive force. How does the attractive force depend on the density? It depends on square of the density, right? Because you need two molecules to have an attraction. So it goes as square of the density, which means it goes as N by V whole square, AN square by V square. So this is our van der Waals equation of state. We also studied virial equation of state, which allowed us to generalize it even further. We talked a little bit about virial coefficients. One big picture in all of these equations, so van der Waals equation of state or virial equation of state, is that they reduce to ideal gas equation of state as rho tends to 0 or as temperature tends to infinity. As you make the density of the system very, very small, you start recovering ideal gas equation of state. Ideal gas equation of state becomes more and more applicable at very low densities or at very high temperatures. At very low temperatures, none of these equations will work very well because quantum mechanics takes hold, right? And those of you who are taking 482 or even the biophysical chemistry equivalent will study quantum mechanics in one form or the other and see what happens there. Quantum mechanics is funky. So we did equation of states. Then we started talking about, okay, and as we did the equation of state, we also talked about thermal equilibrium and mechanical equilibrium. We said thermal equilibrium is when temperature is constant everywhere. Mechanical equilibrium is when pressure is constant everywhere. Later in this semester, we talked about chemical equilibrium, where the chemical potential was constant everywhere, right? So we left chemical equilibrium till much later because chemical potential is an abstract concept. It took us some time to get till there. So at this point, we started talking about first law of thermodynamics, and which is essentially a restatement of energy being conserved. We said that if you take a system and change the internal energy, if internal energy came later, we said if you give a certain heat to a system, if you give delta Q heat to a system, and you do delta W work on the system, this is going to be path dependent. It depends on how exactly you gave heat to the system. W is also going to be path dependent, depends on how did you do work on the system. Their sum is, however, always going to be path independent. And the sum, this was our definition of the internal energy U, which is a state function. This was our first introduction to state function, and this was first law of thermodynamics. At this point, we tried to spend some time looking into delta W. We talked about how delta W can come from, or so, and in differential form, it can be written as du is equal to delta Q plus delta W. So we spent some time talking about delta W. We classified delta W in different ways. We talked about delta W as expansion work or compression work and all other types of work, right? So for a long time in this class, we focused on only when delta W is equal to minus P external dV. Don't forget the P external. When you are doing work under equilibrium, then P external can be replaced by the pressure coming from equation of state. But if you're not doing work under equilibrium, then it is the external pressure that is being applied. So for example, as I'm opening this container and I'm changing the pressure, that does not mean the pressure of the molecules inside is the same. They are trying to adapt to that. So maybe there is a lag, right? If I'm doing it very, very slowly, then it's possible that molecules inside are adjusting their pressure gradually, and I can use the same pressure, right? So we said reversible work is when P external is equal to P system. You are doing the work under condition of mechanical equilibrium, then it's reversible work that is being carried out. And then we talked a lot about, so this was work, then we talked about heat. How does heat given to a system change? For delta Q, we defined two types. We were interested in two types of heat given to the system. We said delta Q could be heat at constant pressure, or delta Q could be heat at constant volume, right? We defined two things. We defined the heat capacity, which was Cp is equal to delta Q. So remember, I'm still writing the squiggly delta because it's not a state function, divided by change in temperature. Whatever change in temperature you did, that could also depend on the path you took, or maybe, yeah, I mean, this is an inexact differential. But we said that this turns out to be the ratio, to be the derivative of a very nice quantity. Anyone remembers what was that quantity? And similarly for CV, so this we are talking about this at constant pressure, and this we are talking about this at constant temperature. So which one was CV? Which state function did we get over here? Partial U by partial T at constant V, right? So this is an equivalent definition of CV. And this is important because if you just look at this formula, it looks like CV should be path dependent, right? The heat capacity of a material should depend on what path did you take in order to heat that material. But that's clearly not true, right? Which chemical has one of the highest heat capacities in the world? Anyone remembers? This is why cities next to this chemical don't have very high temperature variation. Water, right? Water has a very high specific heat capacity, but you report one number for the heat capacity of water. You don't say different numbers. There is another, and on the opposite end, which chemical or material has one of the lowest heat capacities? And cities around this type of material tend to have huge temperature fluctuations. Huh? I heard something. Nothing? Sand. So cities in the desert tend to get very hot during the day, and they can also get very cold during the night. You will have 25 Fahrenheit in the night and maybe, I don't know, 120 Fahrenheit during the day. So, but the point is that the heat capacity is not path dependent. It's a state function. And this one over here is partial H by partial T at constant P. So you still have to account for the constant P, but otherwise it is the change of a state function. And this is when we talked about H. Anyone remembers what was the formula for H in terms of U? U plus PV, it's not U minus PV, right? And the reason we introduced H was, so where did all of this come from? We said that, so if you think about first law of thermodynamics, it says delta U is equal to delta Q plus delta W, right? Or du is equal to delta Q minus PdV. So if, assuming no other work, only pressure volume work, if dV is equal to 0, then du is equal to delta Q, right? This is why the heat capacity at constant volume is the partial derivative of internal energy. If dP is equal to 0, if it's a constant pressure, then dH is equal to delta Q, where H is U plus PV. And that basically explains these two formula, which are very important. Any questions about this? Which one is larger, CP or CV? CP is larger. For an ideal gas, you can prove that CP minus CV is equal to NR. For a non-ideal gas, CP minus CV will not be equal to NR. It will be some other thing. It will be more than 0. And in some of the homework, we derived expressions for what it will be, right? The most general expression for this involves a derivative of entropy with respect to something else. So far, we had not talked about entropy, but we saw some relations. So we can calculate the exact value of CP minus CV for any material, and we did it in a different way. And there is a physical explanation for why CP is more than CV, because as you are giving heat to the system at constant pressure, the system is expanding, right? At constant volume, it's not expanding. At constant pressure, as you give heat to a system, this can expand and do work against the environment. So not all of the heat is going into changing the temperature of the system. Some of the heat is being used to do work against the environment. And that's why CP is always more than CV. It takes more heat to change the system's temperature by a certain amount. At somewhere before this point was the first homework where all of you got pretty pissed off about the number of degrees of freedom, and everyone got very excited how to calculate number of degrees of freedom for different molecules. I'm not going to have you calculate those in the exam. If there is a molecule for which there is a certain number of degrees of freedom, I will tell you what it is. It's really under the purvey of 482 that you look at different molecules and think about how many degrees of freedom you have. But a big picture here was that the U, internal energy, is equal to number of degrees of freedom multiplied by KT by 2, right? This is very well within the range of Chem 481. And this was what we called equipartition. So for an ideal gas with n point-like atoms moving in 3D, in 3 dimensions, U becomes 3n kT by 2, right? So for an ideal gas, if you calculate CV, it's going to be partial U by partial T at constant volume. It becomes 3nk by 2. It's a constant, right? Which is not always true. This led us to think about U as a function of temperature and volume. So we said that if something is a state function, it means we need all values of the state variables, right? We need value of the P, T, V, N. But we know at equilibrium, we don't need all 4, right? So we remove this. So in general, to describe U or any state function, we need all 4 variables, right? We need to characterize the state. then we can talk about a function of the state. However, at equilibrium, we can say that, well, maybe we can write pressure, temperature, and volume as a function of temperature, pressure, number, and number. So we need only 3 values here now: pressure, temperature, and number. But then if you're thinking about constant composition system, which we did for a long time, then N is no longer needed, and we are just left with pressure and temperature, right? We could do a similar thing, and we could just have been left with U as a function of volume and temperature, right? So for a generic system, in order to describe a state function, you need 3 variables due to equilibrium. If you have a constant composition system, you need only 2 variables. We talked about U as a function of volume and temperature for a while, even though later we talked about natural variables. To talk about natural variables, we needed integrated first and second law. And this led us to think about du is equal to partial u by partial v at constant t at dv plus partial u by partial t at constant v dt. For an ideal gas, this is 0. This is CV for anything. Therefore, du is equal to CV dt for ideal gas. Du is equal to pi t dv plus CV dt in general. This is something worth remembering. It's very tempting to calculate du by using CV dt for anything, but that's not true. You need to know the equation of state in order to calculate. If it's an ideal gas, then getting du is quite easy. And this is the complication of partial derivatives, right? Just because CV is partial u by partial t at constant v does not mean that du is equal to CV dt, right? That is true only for an ideal gas. We did a similar business for the enthalpy. We wrote enthalpy as a function of 2 variables. We talked about something called Joule-Thomson coefficient. The same idea for an ideal gas, it becomes very simple. For a non-ideal gas, it's complicated. Okay. We did a bunch of stuff for calculating du, dq, dw for different type of processes, right? Go along a path A in a pressure volume diagram, you go along a path B in a pressure volume diagram. And we played with all that, we mastered all that. Now we started thinking about, is first law of thermodynamics really sufficient to describe everything? And then the point came that if you have an egg and you drop the egg on the ground and it breaks into 50 different pieces, for that you can show that the change in internal energy is equal to the heat given to the egg plus work done on the egg in order to break it. But now imagine the reverse process in which the egg randomly jumps up from the ground in its 1,000 different pieces and reassembles itself. For that, you will have minus delta U is equal to minus delta Q minus delta W, the opposite of the previous process, right? This is when egg breaks, and this is when egg reforms. We did not do it for an egg, we did it for a ball bouncing back, right? And we thought about how the ball bounces back up. And we realized that first law of thermodynamics allows both. And that's not, there is something is missing. That led us to the notion of second law of thermodynamics, where we introduced the concept of entropy. And we said that for a spontaneous process, so in this case, this is spontaneous process. The breaking of the egg is one where the entropy of the universe, which is the entropy of the system plus entropy of the surrounding, must increase. This was our first definition of second law of thermodynamics, or maybe third definition. We had few other definitions, right? We had the Clausius statement, we had the Kelvin statement. We said heat cannot spontaneously flow from a cold body to a hot body, right? You have to do some work on it. And the most important thing here was we said that this S is a state function. So we defined S in 2 different ways. The first way to define S was to say that while the heat given to a system is going to be a path function, even if you're doing reversible change on the system, the heat given to a system is going to depend on how that reversible process was carried out, right? So we always have a delta Q. But if you divide it by T, then you get a state function, right? We did it by drawing some pressure volume diagrams. Remember, we did it in class. We had 5 different diagrams, 5 different paths, and we calculated the entropy change along all of them by using this formula. And we saw indeed entropy is the same. We then looked at a general proof of it by introducing the concept of a Carnot cycle, where we showed that entropy change for we broke it in 3 different parts, right? And we introduced a Carnot cycle, and we showed that this is a state function for an ideal gas undergoing a special cycle known as the Carnot cycle. Then we said this is a state function for any gas undergoing a Carnot cycle. And then we showed it is a state function for any gas, any cycle, right? And that was our proof. We also had another formula for entropy, which was S is equal to K log W. We did not really use it. I mentioned it, and it's sometimes quite useful. It's one of those formulas that somehow students forget everything in 481 and then remember this formula somehow. This is Boltzmann constant K, and where W is the number of ways of arranging to a system. So currently this is in a high entropy state, everything is scattered. If I allowed everything to be only in one corner, nicely stacked, then W is 1 and entropy is equal to 0, right? And they both things are consistent with each other. And we said that S as T tends to 0 goes to 0. And this was our third law of thermodynamics, which basically means that at the ground state, at 0 temperature, there is only one ground state. There is only one unique minimum. So W is equal to 1, therefore S is equal to 0. So this was our third law of thermodynamics. We spent a lot of time talking about different formulations of second law of thermodynamics, not just the Kelvin statement and Clausius statement, but we introduced different formula for it. So we talked about Clausius inequality, and you can read on that. But what I really want to mention here is that just related to Clausius inequality, we introduced 2 more state functions now. One was called Gibbs energy, G. What was the symbol for Gibbs energy? Did we use G? Okay, I have forgotten already. Semester end. And what did you use for Helmholtz? A or H? Yeah, some books use A, H. Some books use F. It's everywhere. So what, anyone remembers the formula for G? H minus TS. And how about A? Huh? U minus TS. Does everyone agree with that? And why were these G and A important? G and A were important because just like we said that ds universe more than 0 for spontaneous process, spontaneous change, equivalent to this is the system that the Gibbs free energy, equivalent to this statement is the statement that the Gibbs free energy of this system at constant temperature and pressure must be smaller than 0. Helmholtz free energy of this change of this system at constant temperature and volume must be smaller than 0. And the very nice thing here is that this is DG system. This is DA system. So you don't have to think about system plus surrounding. If it's a constant temperature process, you can just look at the free energy of the chemicals that are sitting in your beaker. You don't have to worry about what's happening in the rest of the universe if it's a constant temperature process. And that's why Gibbs free energy is so important, right? Anytime you have an open beaker reaction going on, you can use it. If you have a closed furnace reaction going on, then you can just use temperature and volume, even though maybe some leakage is happening through the furnace. Who cares? It's fixed volume. So you can use Helmholtz energy. This, for those of you, I mean, many of you, you're all going to have STEM degrees, and not all of you will be professors. Some of you will be working in industry, doing variety of things. You will maybe be working in the battery industry, in the polymer industry, in the pharma industry. which free energy to use is something people take very casually, and it often leads to huge mistakes, huge miscalculations. Billions of dollars probably get wasted because people did not consider the right free energy. If you are looking at a battery, the free energy that you consider in a battery is going to be different from the free energy that you consider in a cell membrane, in an open cell, for example. All you need to think about is it constant temperature pressure or is it constant temperature volume? Otherwise, everything else is same. And notice that while the entropy must go up, the free energy must go down. This is something students forget every once in a while. It's something you should try to remember. Okay, then, so we had our du is equal to delta Q minus PdV. And we said ds is equal to delta Q reversible by temperature. So we mixed both of these to introduce the most important equation in Chem 481, which is the integrated first and second law of thermodynamics. du is equal to TdS minus PdV. This is a very good point to start talking about chemical potential. So far, we did not really worry about what happens to the change, what happens to the internal energy or some state function if you change the number of species in this system, right? So if you think about this thing, what are the variables for U over here? S and V. And this is why we call them as the natural variables for U. However, these two natural variables came in a constant composition system, right? If you have a variable composition system, then you have to think about du is equal to TdS minus PdV plus whatever happens to du with change in number of species of every different component, right? And that one we call mu I. So mu I here can be defined as partial U by partial Ni at constant entropy and volume and all other concentrations constant, right? So this is the most general form of the integrated first and second law of thermodynamics. And now you can see the natural variables for internal energy are S, V, and N. We then put in the formula for G. We use the formula for G, which is H minus Ts, or H is equal to U plus PV minus Ts. And we calculated similar expressions for G. Anyone remembers what we got for G? Go ahead. VdP minus SDT plus mu I dNi. So let me write this down on the next page. We got du is equal to TdS minus PdV plus mu I dNi, where mu I is equal to partial U by partial Ni at constant entropy and volume and all J not equal to I. And for dG, we get VdP minus SdT plus mu I dNi. And if you think about it, this mu I now is partial G by partial Ni, keeping other things constant. In this case, it is keeping pressure, temperature, and J not equal to I constant. However, it's the same mu I. It does not matter which thing you differentiate. We showed it that it is the same mu I. Similarly, we could, and so this leads us to the natural variable for G. Those are pressure, temperature, and number. Similarly, we did things for A, we did things for H. We defined natural variables for all of them. One of the other things we did with this equation, let's just look at du is equal to TdS minus PdV. We said this is an exact differential, right? So this means that if partial T by, I really have to move over it faster, so I'll just write down the key idea here. This is exact differential, which led us to derive the Maxwell relations, right? Which was a connection between the partial derivatives. And we did that for du, we did that for dg, we did that for dh, we did that for dA. From all of them, we got a bunch of Maxwell relations. They are hard to remember. There are some mnemonics for Maxwell relations that you will find on the internet. The most important thing is to remember this equation. If you remember this one, and if you remember the definition of G, H, and A, you can derive everything. It will take a bunch of algebra, but you can derive it all. This is the relation that you should not forget. The Maxwell relations were quite important. We did a bunch of things with them, but the key idea is they came out of these partial derivatives. We spent a lot of time talking about chemical potential. We used chemical potential to basically understand what happens in a system as change occurs in the chemical composition, right? So just like if you have something at a hotter temperature and something at a cooler temperature, heat will flow from the direction of hotter temperature to cooler temperature until the temperature becomes constant. Same thing happens with chemical equilibrium. If you have higher chemical potential, if you have higher chemical potential and lower chemical potential, you will move from the higher chemical potential to the lower chemical potential until the chemical potential becomes equivalent. So it's very abstract if you think about it. I mean, you go on the street and tell someone, oh yeah, I mean, the temperature is kind of hot today, and there will be, no one really thinks about what's temperature, right? We take it obvious. And if you tell someone, oh, the chemical potential is a bit hot around here, we're like, what a weirdo, right? And they're like, no, let me explain to you what is chemical potential. It is just the partial derivative of U with respect to N at constant entropy volume and other N being constant. They're like, even weirder. So definition is a bit complicated, but it's really simple. It is just like temperature does for heat, chemical potential does for mass. Okay, that's the whole idea. Now, we used chemical potential. We used chemical potential to talk about phase boundaries, right? We talked about phase diagrams. We talked about the simplest phase diagram we talked about was water, right? For water, does anyone remember what were the coordinates of the phase diagram? It's single composition, same composition. So what were the coordinates? Pressure, temperature. What was the x-axis? Huh? Are you sure? And okay, if I'm wrong, you can blame Ryan. But let me not claim this is water. This is some substance, okay? And we can talk about the single composition phase diagram, and we can talk about these boundaries, right? So the boundaries, so let's say this is some phase alpha, and this is some phase beta, and this is some phase gamma, okay? Some phase, maybe alpha is solid, maybe beta is liquid, I don't know. Maybe all three are solid. This line corresponds to the coexistence of beta plus gamma. Along a line, mu beta is equal to mu gamma. Along this line, mu alpha is equal to mu gamma. And this point, which is a triple point, is mu alpha is equal to mu beta is equal to mu gamma. We talked about the slope of the line, right? We talked about how the slope of the line should look. In order for that, we said dg is equal to 0 is equal to v dt minus s dt, keeping composition constant in a single composition system. Therefore, and so we derived our Clausius equation and Clausius-Clapeyron equation out of this idea that allowed us to talk about the boundary of the phase, about the slope of the phase boundary. We studied how the slope of the phase boundary for different phase changes looks like. Remember, we talked about solid liquid change, we talked about solid gas change and liquid gas change. The phase boundary is very steep for one of them. For the other two, it is kind of boring, and that came from the properties of the delta V in that. We used it to think about ice skating, where I showed you it's still quite complicated. It's not just localized melting, which can explain ice skating. So We also talked about Gibbs phase rule, which is F is equal to C minus P plus, how much? Huh? 2, okay. Different books write it different way. So we use this to explain that for a single component, we derived it by thinking about the balance of chemical potential. And we used it to explain why in a single component system, at best, you can have a triple point. You cannot have a quadruple point. If you have a 2-component system, you can have a quadruple point. One thing I also want to mention here is that G is equal to mu times N for 1-component system. This is not true for A. A is not equal to mu times N. H is not equal to mu times N. Why does this happen? This happens because we showed this when we talked about partial molars, right? And we showed that partial molar is defined. Yeah, so we showed that mu has a very special connection with G. It does not have that special of a connection with anything else. It gives free energy. It has this very special connection. So in fact, another way of thinking about the chemical potential is Gibbs energy per mole in a constant composition system or a single element system. Okay, if you have no variable in composition or the composition is indeed constant, then it is just Gibbs free energy per mole. Otherwise, G is equal to mu1 n1 plus mu2 n2 plus mu3 n3. We could not write similar equations for Helmholtz and enthalpy if we had this special relation for G. We spent a lot of time talking about phase diagrams on the basis of this. I just drew one phase diagram here. We looked at other phase diagrams. We spent a lot of time talking about mixing, what happens in ideal mixing, what happens in non-ideal mixing. We had ideal mixing, we had regular solution mixing, and then we had generalized mixing, right? So ideal mixing was when delta H mixing is equal to 0, delta S mixing is equal to XA log XA plus XB log XB. Did I forget a minus sign here? Check. Okay. For regular solution mixing, we said delta S mixing is the same as delta S mixing for ideal, but we allowed this to change. We made this as omega XA XB, where omega was the regular solution parameter. We did not really talk a lot about general solution. I'll finish in 2 minutes. I know our time is up. I'll finish in 2 minutes. We did not talk about much about real solutions. I just said this framework can be used. It's quite general, real solutions. Whenever we had to talk about real solutions, we talked about things like mu is equal to mu naught plus RT ln XA. So let's say mu A is equal to mu A naught plus RT ln XA. And we would say, well, this is true for an ideal mixture. For a general mixture, this is not going to be true. So we will just call it as the activity, ln AA, for real mixture. And then we talked about activity coefficients and things. In the exam, I won't bother you with real mixtures. At best, we will definitely talk about, we will go beyond ideal gases. So we will talk about van der Waals gases and virial equation of state. You could have problems on that. You could have problems on the regular solution model. The real world, which goes beyond regular, all you need to remember is you introduce things which help you follow such equations. And finally, we talked about equilibrium constant, which is the very last topic, which is on the exam. There we said that delta G is equal to delta G naught plus RT ln P by P naught. And we said at equilibrium, this is equal to 0. So we talked about Q, which is, this led us to the concept of Q, which is the reaction quotient. And we said at equilibrium, Q becomes K, which is the equilibrium constant. Using that, we explained how equilibrium shifts by increasing temperature or pressure, or by decreasing temperature or pressure. That was the last topic in the class. We did a bit of kinetics. That's not going to be on the exam. If you have any questions about this semester, you can ask me on Slack. I'm lazier on the weekends. I have a lot of TV to catch up on. So, but I will try to reply. You will, and if post on general, please take help from your friends, post on general, and I will try to reply. Starting Monday morning, I will not, once the exam is out, I will be replying only for possible typos. So good luck. And please finish up the course well. Otherwise, it was wonderful having you all. And 2 teams are going to get ice cream. I will get back to you about that soon.